February 1943. The scorching deserts of Tunisia. A lone American tank sits motionless in the sand, its white star barely visible beneath a freshly painted German cross. Around it, officers from Heavy Panzer Battalion 501 gather with notebooks clutched in their hands, their faces a mixture of curiosity and professional skepticism. They have no idea that this single vehicle, captured intact during the chaos of the Battle of Sidi Bouzid, is about to trigger an engineering crisis that will haunt the Third Reich till its final days. This wasn't just another captured enemy tank, destined to be scrapped for intelligence, photos, and a few measurements. This was something far more dangerous to German confidence. This was proof, written in steel and automotive engineering, that everything the Wehrmacht had believed about American industrial capability was catastrophically wrong. The story you're about to hear isn't. It's about which tank had the thicker armor or the bigger gun. Those debates miss the point entirely. This is about something far more fundamental. Something that German engineers would spend 2 years testing, retesting, and ultimately being forced to admit the Americans had built reliability into their tanks that German industry simply could not match. And in the brutal mathematics of mechanized warfare, a tank that reaches the battlefield beats. It's a superior tank that breaks down before the fight every single time. The tank bore a name painted in white letters across its hull. War Daddy 2, serial number USA 3,067,641, built by Lima Locomotive Works in Ohio. Assigned to Company G of the 1st Armored Regiment, 1st Armored Division, to the Germans who captured it, this was a trophy. To the engineers who would soon examine it, this would become an uncomfortable mirror reflecting everything wrong with their own designs. A German reconnaissance unit. Likely as surprised as anyone to find an intact American tank. Drove this Sherman 350 kilometers across North African terrain to the port of Sfax. Think about that for a moment. 350 kilometers. Through desert sand, over rocky terrain, in the unforgiving heat that had already proven lethal to so many German vehicles in North Africa. The journey took 4.5 days. And here's where the story gets interesting. During those 4.5 days, something remarkable happened. Or rather, something remarkable didn't happen. The engine never overheated, not once. The transmission never failed. The final drives maintained consistent performance kilometer after kilometer. For the German soldiers accustomed to nursing their temperamental panthers and tigers through even short movements, this was nothing short of bewildering. German tank crews knew mechanical failure intimately. They knew the sinking feeling when the transmission made that grinding noise that meant you'd just lost third gear. They knew the careful throttle management required to prevent overheating. They knew the constant stops to check fluid levels, adjust track tension, pray that the final drives would hold together for just one more mission. They had accepted these as unavoidable realities of armored warfare. The price paid for powerful, sophisticated machines. But this American tank just worked. Mile after mile, it simply refused to break. No drama, no constant mechanical coddling, no specialized knowledge required. It ran like a truck. And that simplicity terrified the German engineers more than any Allied superweapon could have. At Sfax, where Daddy 2 was loaded onto a cargo ship bound for Germany, the Army Weapons Office had issued explicit, urgent orders. This tank must reach the testing facility at Kummersdorf intact and operational. Someone high up in the German command structure understood that this vehicle represented something more significant than a single battlefield capture. It represented American industrial philosophy made tangible, and that philosophy needed to be understood. German intelligence had been receiving fragmentary reports about American tank production for months. Numbers so large they seemed impossible. Claims of standardization and interchangeable parts that seemed too good to be true. Statistics about production rates that suggested America was building tanks the way they built automobiles, by the tens of thousands, with civilian automotive workers using civilian manufacturing techniques, but numbers on intelligence reports remained abstract. Easy to dismiss as exaggeration or Allied propaganda, this physical vehicle, however, made those statistics real in a way that paper never could. You could touch it. You could measure it. You could drive it. You could tear it apart and see exactly how it was made. And when you did all those things, the truth became unavoidable. As the ship steamed northward across the Mediterranean, Wehrmacht engineers at Kummersdorf prepared testing protocols that would be more comprehensive, more rigorous, and more scientifically thorough than anything they'd applied to their own designs. They would subject this American tank to every test they could devise, measuring and documenting everything. They would approach this examination with characteristic German thoroughness and precision. And in doing so, they would discover truths about their own, limitations that some of them had suspected but none had wanted to confront. Directly War Daddy 2 rolled off the transport rail car at Kummersdorf bearing the designation Butterfahrzug 259 and German license plate WHO 58941 the moment it arrived. Test engineers swarmed over it like archaeologists examining an artifact from an advanced civilization. They stenciled armor thickness measurements across every surface. They marked angles with precise notations. They photographed it from dozens of perspectives, creating a comprehensive visual record. Kummersdorf Proving Ground, located about 25 kilometers south of Berlin, served as the primary testing facility for captured Allied equipment. This wasn't some makeshift operation. This was German engineering at its most methodical, staffed by some of the Reich's best automotive and weapons specialists. These men understood vehicles. They understood stress analysis, metallurgy, powertrain dynamics, and all the theoretical frameworks that undergirded armored vehicle design. What they were about to learn was that sometimes theory and practice diverge in ways that academic knowledge cannot bridge. The initial inspection was conducted by multiple teams of specialists, each examining their area of expertise. Powertrain engineers focused on the transmission and engine. Armor specialists measured plate thickness and examined welding quality. Weapons experts evaluated the gyro-stabilized gun, a feature so advanced that the public assessment in Das Reich newspaper would later call it the first attempt of its kind ever to be made anywhere. Suspension. Engineers studied the track system and bogies, but it was the transmission that caught immediate attention and held it. German engineers gathered around this component like medical students around a particularly interesting specimen. What they saw challenged fundamental assumptions about what was possible in mass production. The Sherman used herringbone-cut gears throughout its transmission. These gears, with their distinctive V-shaped teeth, distributed stress across multiple teeth simultaneously. This meant that minor imperfections in individual teeth didn't cause catastrophic failure. The gears were quieter, smoother, and far more durable than the straight-cut gears German tanks employed. Now, here's the thing. German engineers knew about herringbone gears. They understood the theoretical advantages. They had considered using them, and they had rejected the idea as impractical because herringbone gears required sophisticated manufacturing capabilities and tight quality control across mass production. Given German industrial capacity and workforce training, they had concluded these gears were simply too difficult to produce in quantity. The Americans had been manufacturing them by the thousands since the 1930s for civilian trucks and automobiles. This wasn't cutting-edge military technology requiring specialized facilities. This was standard American automotive practice, applied to tank production without any apparent difficulty. The transmission also featured 5 forward speeds plus reverse, with synchronization in gears 2 through 5. If you've ever driven a manual transmission car built after the 1960s, you've experienced synchronized gears. They allow smooth shifting without the double-clutching technique that earlier transmissions required. For tank crews, this meant the Sherman drove almost like a civilian vehicle. Any soldier with basic automotive knowledge could operate it competently after minimal training. German tank transmissions require drivers to master double-clutching, careful rev matching, and precise throttle control to avoid damaging the gears. This wasn't because German engineers didn't understand synchronized transmissions. It was because implementing them at scale, with the reliability standards American civilian industry demanded, exceeded German manufacturing capabilities during wartime conditions. Think about what this meant operationally. The Sherman could be driven by conscripts with a few weeks of training. The Panther required skilled drivers who understood the temperamental nature of their machine, who knew that third gear was fragile and should be avoided when possible, who had internalized the complex interplay of clutch, throttle, and gear selection required to keep the transmission alive. Which army could field more tank drivers? Which design philosophy made sense when you needed to crew thousands of tanks? The actual testing program began with basic automotive trials designed to stress every mechanical system. Engineers drove War Daddy 2 through obstacle courses that replicated battlefield conditions. They measured fuel consumption under varying loads. They monitored engine temperatures continuously. They recorded transmission behavior during acceleration, climbing, turning, and sustained high-speed operations. After each trial, they disassembled components to examine wear patterns. They looked for signs of stress, concentration, inadequate lubrication, material fatigue, or design weaknesses. They measured bearing wear, checked for metal particles and lubricants, and used precision instruments to detect any degradation in component dimensions. The results contradicted everything German tank doctrine had accepted about necessary trade-offs between performance and reliability. The Sherman performed adequately in most categories. Not spectacularly, not poorly, just adequately. Its armor protection was reasonable, but not exceptional. Its gun was effective against most targets, but nothing special. Its speed and maneuverability fell within expected parameters for a medium tank, but in one critical metric, it didn't just excel. It redefined what German engineers thought was achievable. That metric was operational endurance without maintenance intervention. German tanks required constant attention. Fluid levels checked daily. Track tension adjusted frequently. Valve clearances inspected and adjusted regularly. Transmission oil examined for metal particles. Final drives monitored for any sign of impending failure. This wasn't considered excessive maintenance. This was just how tanks operated. You accepted it the way you accepted that aircraft needed mechanics between flights. The Sherman just kept running. Kilometer after kilometer, day after day. Operating at a tempo that would have destroyed German powertrains in short order. The testing logs from Kummersdorf document operational ranges, exceeding 2,000 kilometers before requiring major maintenance. 2,000 kilometers. Panthers in early 1943 were being abandoned after less than 200 kilometers when their final drives failed. Let that sink in. The American tank could operate 10 times longer between major maintenance than the German tank that was supposedly superior in every technical specification. The Continental, our 975 radial engine in war. Daddy 2 demonstrated remarkable tolerance for varied operating conditions. This engine, originally designed for aircraft use and adapted for tanks, maintained consistent performance across temperature ranges that would have caused German engines to either overheat or lose significant power. The cooling system, though elegantly simple in design, proved highly effective even in the simulated desert conditions. The Germans imposed during testing, the air filtration system handled fine dust without clogging, a capability that would have saved countless German vehicles in North Africa had their designers prioritized it. Every system, from electrical to hydraulic, reflected a design philosophy that valued practical functionality over theoretical optimization. German engineers found themselves writing reports that must have been professionally painful. These were men who had spent careers pursuing engineering excellence, who understood sophisticated technical concepts, who could calculate stress loads and thermodynamics with precision. And they were being forced to acknowledge that American engineers who seemingly just wanted their tanks to work, like trucks, had produced something fundamentally superior. The 6th and 7th of June, 1943, brought a moment of public reckoning that many German officials would rather have avoided. Reich Minister Albert Speer arrived at Hillersleben artillery range to preside over a major armaments conference. Speer, responsible to Hitler himself for armaments production, needed to understand what American industry could actually produce and how German designs compared. The demonstration program included hill climbing trials comparing German and captured Allied tanks. This wasn't supposed to be a contest. It was meant to be a scientific evaluation of comparative capabilities. But when you put vehicles side by side and ask them to perform the same task, Comparisons become inevitable. War Daddy 2 sat alongside Germany's latest designs. Next to it, a Panther Ausführung D, fresh from production with all the improvements that had been frantically implemented after early combat disasters at Kursk. Beyond that, a Ferdinand tank destroyer representing Germany's most advanced armored fighting vehicle technology. 65 tons of steel, armor, and firepower, equipped with a sophisticated electric transmission system that seemed impressively futuristic on paper. The Sherman climbed the test slope smoothly. Its driver shifted through the gears with confidence, the synchronized transmission making the task almost boringly easy. The engine maintained consistent power delivery, never faltering. The vehicle reached the top without drama, turned around, and descended under complete control. The Panther followed. Its more powerful 700 horsepower Maybach HL230 engine allowed it to match the Sherman's performance. But just barely, and with considerably more difficulty. The driver's careful throttle management and precise gear selection revealed the delicate nature of the vehicle. This wasn't a truck. This was a temperamental thoroughbred that required constant attention and skill too. Operate successfully. Then came the Ferdinand's turn. 65 tons of German engineering sophistication began climbing the slope. Partway up, the electric transmission system, which had seemed so innovative in design specifications, simply gave up. The massive vehicle stalled, its engine unable to deliver power to the tracks. Recovery crews rushed forward, attempting to restart the immobilized tank destroyer, while dozens of senior officers and industrial leaders watched in uncomfortable silence. Albert Speer, standing among those officers, witnessed German armor humiliated by a captured American tank that had probably cost half as much to produce and required a fraction of the manufacturing sophistication. This wasn't an isolated incident. This was a pattern that Speer would see repeatedly throughout the war. Years later, in his memoirs, Speer would write about Sherman capabilities. Observed during an inspection tour of Italy in October 1944, he noted that reports on the country mobility of the Sherman had been very favorable. The tank, he wrote, could climb mountains that German tank experts had considered inaccessible to armored vehicles. He attributed this to the Sherman having a very powerful motor in proportion to its weight, giving it mobility on level ground that's definitely superior to German tanks. These weren't the words of a propagandist trying to demoralize the enemy. These were the private observations of Germany's armaments minister, the man responsible for keeping the Wehrmacht equipped, admitting in writing that American tanks performed better than German designs in fundamental ways. The public assessment appeared in Das Reich newspaper on June 27, 1943. Carefully worded article called The Sherman, one of the special accomplishments of the North American laboratories, and described it as quite a praiseworthy product of the North American steel industry. Peace noted that the first things to attract attention were serial construction and fulfillment of the almost arrogant requirements of the North American automobile industry. Read that phrase again. The almost arrogant requirements of the North American automobile industry. This was German engineering pride coming face to face with American industrial maturity. The arrogant requirements were simply that vehicles should work reliably, require minimal, specialized maintenance, and use interchangeable parts that any competent mechanic could replace. These weren't arrogant. These were the baseline expectations of an industry that had been mass-producing vehicles for civilian customers for decades. But two German military engineers, accustomed to accepting frequent breakdowns and complex maintenance as unavoidable realities, these standards seemed impossibly high, arrogant even. Back at Kummersdorf, systematic testing continued through the summer and into autumn of 1943. Each test generated more data. Each measurement added to a growing body of evidence that became increasingly impossible to rationalize away or dismiss as testing anomalies. Engineers measured operational range under various conditions. They conducted extended trials that pushed the Sherman to its limits, driving it continuously for days, tracking every aspect of its performance. They documented operational ranges exceeding 2,000 kilometers before major maintenance became necessary. For context, early model Panthers were being abandoned in the field. After traveling barely 100 kilometers, when their final drives failed catastrophically, they measured transmission efficiency, calculating power losses through the drivetrain. The Sherman's synchronized manual transmission lost significantly less power between engine and tracks than comparable German systems. This meant more of the engine's output actually reached the ground, translating into better performance. Without requiring a more powerful engine, they examined the final drives with particular attention because German final drives had become a crisis point in their own tank designs. The final drive is what transfers power from the transmission to the drive sprockets that turn the tracks. It's under enormous stress, especially in heavy tanks. Get the design wrong, vehicles become immobilized far from any repair facility. German Panther tanks employed final drive systems inherited from the Tiger design. These used straight-cut gears and housings that proved inadequate for the loads imposed by the 45-ton vehicle. German mechanics in North Africa and on the Eastern Front had been reporting final drive breakdowns with alarming frequency. Panthers were being abandoned after traveling distances so short that commanders began restricting their movement to preserve them for actual combat rather than losing them to mechanical failure during approach marches. The Sherman's final drives, built using the same herringbone-gear principles as the transmission, rarely failed even under sustained combat conditions that would destroy German components. Decades later, restoration projects would discover Sherman final drives that needed no mechanical restoration after years of storage, testament to design margins that exceeded immediate requirements by substantial factors. This overbuilding, this incorporation of safety margins beyond what seemed immediately necessary, represented a fundamental philosophical difference. German engineers calculated components precisely, designing them to handle expected loads with minimal excess capacity. This seemed efficient, avoiding waste of scarce materials. American engineers built in margins, accepting higher initial material costs in exchange for reliability and durability over the vehicle's service life, which philosophy made sense. When you needed vehicles that would operate under unpredictable battlefield conditions, maintained by crews with varying skill levels, using whatever fuel and lubricants were available, in climates ranging from African deserts to Russian winters. By late 1943, Kummersdorf had accumulated enough data to produce comprehensive internal reports that circulated through Wehrmacht technical branches. These documents, intended for senior Wehrmacht officers and armaments ministry officials, painted a sobering picture that became increasingly difficult to ignore. The Sherman demonstrated American automotive engineering maturity that Germany fundamentally lacked despite its theoretical knowledge and scientific expertise. Mass production techniques allowed tolerances that would be considered sloppy in German precision manufacturing, yet resulted in more reliable vehicles that functioned better under field conditions. Interchangeable parts meant field repairs could be accomplished with basic tools and minimal specialized training, while German vehicles required factory-level precision and specialized equipment for many repairs. The entire design philosophy prioritized keeping vehicles operational rather than achieving theoretical performance maximums that looked impressive in specifications, but couldn't be maintained in combat. Internal German engineering assessments began documenting observations about American industrial advantages that went far beyond simple production numbers. The truth was becoming clear, even if many were reluctant to state it directly. American automotive engineering reflected decades of civilian industry experience that Germany had never developed at comparable scale. Before the war, the United States had widespread automobile ownership. Cars were commonplace among ordinary citizens across all economic classes. In 1940, there were more than 30 million registered automobiles in America for a population of about 130 million people. That's roughly one car for every 4 people. Germany, by contrast, had far more limited civilian automotive experience. Cars remained luxury items for the wealthy and party elite. The Volkswagen program has promised to German workers since 1934 as the people's car. that would make automobile ownership accessible to ordinary citizens. Had delivered fewer than 1,000 civilian vehicles by 1939. The rest went to military applications or remained unbuilt. This vast difference in automotive industry maturity translated directly into tank design philosophy. Americans built tanks that mechanics with civilian automotive training could maintain using skills they already possessed from working on cars, trucks, and tractors. Germans built tanks that required specialist training and constant expert attention from personnel with years of specific military technical education. The Shermans. Design borrowed heavily from civilian automotive. Practice because its designers. Engineers from General Motors, Ford, and Chrysler thought like automotive engineers. They used proven components from their civilian product lines wherever possible. They designed for ease of manufacturing because they understood that hundreds of different factories would need to produce parts and subassemblies. They planned for field maintenance because they understood that vehicles break down and that keeping them operational mattered more than theoretical. Perfection. German tank designers thought like weapons engineers. They optimized for performance specifications that would look impressive in briefings to senior officers. They accepted complexity because sophisticated systems demonstrated technical prowess. They designed for factory conditions because they assumed that vehicles would return to specialized facilities for major maintenance. These different approaches produced exactly the results you'd expect. American tanks that worked like robust commercial vehicles. German tanks that worked like experimental prototypes that had never quite been refined for mass production. The comparison with German tank reliability became impossible to ignore as field reports accumulated through late 1943 and into early 1944. Numbers don't lie. And the numbers coming back from every front told the same story. Panther tanks required strict operational restrictions to prevent mechanical failures. Drivers received explicit instructions that read more like warnings than guidance. Don't change gears frequently, because excessive shifting damages the transmission. Avoid using third gear except when absolutely necessary, because it breaks under stress. Don't turn while backing up, because this destroys the transmission. Only perform pivot turns when ground resistance is equal on both tracks, severely limiting tactical flexibility. Foreign objects entering the running gear can jam the drive sprocket, requiring hours of maintenance to clear. These weren't temporary problems with early production vehicles that would be resolved through minor improvements. These were fundamental design limitations that persisted throughout the war. Despite continuous efforts to address them, Panther operational readiness averaged below 40% through most of 1943. Think about what that means. In an average Panther battalion, fewer than half the tanks were actually capable of combat operations on any given day. The rest sat broken down, awaiting parts or undergoing repairs that required specialized equipment and trained mechanics. Some units reported catastrophic rates as low as 20 to 25%. Individual Panther battalions documented periods when fewer than 1 in 5 tanks were operational. You can't fight a war with those numbers. You can't maintain offensive operations. You can't even maintain defensive positions effectively when 3/4 of your armored vehicles are sitting in repair depots. Specific data from German field reports documented the Panther reliability disaster in devastating detail. During Operation Citadel at Kursk in July 1943, Panthers achieved only 16% operational readiness. 16%. Mechanical failures eliminated more tanks than Soviet action during the largest tank battle in history. By December 1943, readiness had improved to 37%. February 1944 showed 37% operational. April 1944 reached 50% operational. May 1944 finally achieved 78%. These figures represented years of engineering improvements, manufacturing refinements, and accumulated field experience. The best operational readiness rate Panthers ever achieved was 78%, and that came nearly a year after introduction and only after desperate Efforts to address the most critical failures, Sherman tanks, by comparison, maintained substantially higher operational availability from initial production. Readiness rates consistently exceeded 80% across all theaters, often approaching 90% in well-supplied units. This wasn't because American crews were better mechanics or because American logistics were only slightly superior. This was because the tanks themselves were fundamentally more reliable. By December 1943, anyone examining the data objectively could see the pattern. It wasn't subtle. It wasn't ambiguous. It was mathematical certainty. Engine lifespan for the Sherman. Diesel variant exceeded 3,000 kilometers under proper maintenance. Panther engine lifespan barely reached 1,000 kilometers, even after improvements addressed the worst early problems. German reports from March 1944 documented that improved Panther engines achieved service life of 700 to 1,000 kilometers. And this was presented as a success worth celebrating. This improvement merely brought Panther engines to roughly one-third of Sherman. Diesel capability Sherman transmissions required minimal maintenance between overhauls. The synchronized gears reduced the likelihood of driver error causing damage. The herringbone-gear teeth distributed stress evenly, preventing the kind of catastrophic tooth failures that plagued German transmissions. Panther transmissions demanded constant attention and frequent repair, with third-gear failures so common that drivers learned to skip from second to fourth gear to avoid using the problematic ratio entirely. Sherman final drives operated reliably under conditions that routinely destroyed Panther final drives within 100 to 200 kilometers of operation. This single component failure was abandoning more German tanks than enemy fire in some sectors. Crews would hear the grinding noise that indicated final drive problems and know they had, at best, a few more kilometers before the vehicle became immobile. In contested territory, immobile meant abandoned. Abandoned meant destroyed to prevent capture. Field reports from German units using captured Shermans reinforced the Kummersdorf testing data with real-world operational experience. German mechanized units, desperate for reliable vehicles as their own tank strength degraded, eagerly employed any captured American tanks they could obtain intact, unlike Soviet T-34 tanks, which Germans extensively modified before putting into service, because they considered the original designs inadequate for their needs. Shermans entered German service without changes. They didn't require modification because they worked correctly as designed with no fundamental flaws that needed correction. German tank crews who had experienced multiple mechanical failures in their own vehicles found the Sherman's reliability remarkable. They commented on it frequently in letters home, in official reports, and in post-war interviews. Consistent. Theme was surprised that a tank could be this dependable. Reports from panzer regiments noted that Sherman operators could focus on tactical considerations and combat effectiveness, while Panther and Tiger crews constantly worried about reaching the battlefield without breakdown or completing missions, before mechanical failure immobilized their vehicles. One particularly telling example came from January 1945 during Operation Nordwind. The 10th SS Panzer Division captured 12 M4A3 Shermans at Herlesheim. These tanks had belonged to the American 43rd Tank Battalion and were captured intact when their crews abandoned them during the German assault. The 12 Shermans were formed into the 13th Company of the 10th SS Panzer Regiment and served in combat operations for the remainder of the war. These captured tanks served as reconnaissance vehicles and mobile reserves, roles that required sustained movement without maintenance, stops, and reliable mechanical performance. German commanders recognized what Kummersdorf testing had proven years earlier. American tanks could be relied upon to function when needed. This dependability, more than firepower or armor protection, determined tactical utility in the final months of the war. A Sherman arriving at the battlefield with a 75mm gun that worked was infinitely more valuable than a Panther with a superior gun broken down 20 kilometers behind the lines. This wasn't theoretical analysis. This was lived experience for every German tank commander in 1944 and 1945. Additional captured Shermans arrived at Kummersdorf through 1943 and 1944. Tanks taken from British units in Italy, vehicles captured from Soviet forces on the Eastern Front who had received them through Lend-Lease, Each captured vehicle underwent similar testing protocols, building a comprehensive database of American tank capabilities across different variants and production periods. The consistency impressed German engineers more than any single vehicle's performance. American industry was producing multiple Sherman variants simultaneously, different engines and different manufacturers, yet every variant demonstrated the same fundamental characteristics: excellent automotive reliability, derived from sound engineering principles and quality manufacturing processes. The M4A1 with the Continental R975 radial engine that powered War Daddy 2, the M4A2 with twin General Motors 6046 diesel engines, the M4A3 with the 4G AAV8 gasoline engine that American crews considered the best Sherman power plant, the M4A4 with the Chrysler 57 multi-bank engine that combined 5 separate engine blocks into a single unit. Every variant worked reliably despite having completely different power plants. The standardization extended throughout the vehicle. The transmission from a Caterpillar-built Sherman could be installed in a Ford-built Sherman without modification. The final drives were interchangeable across all variants. The suspension components could be mixed freely. Track links from one manufacturer fit perfectly on vehicles from another manufacturer. This wasn't just good practice, this was manufacturing capability that German industry had never achieved at scale. German Panther tanks built by different manufacturers had subtle variations that prevented true parts interchangeability. A transmission from a man-built Panther might not fit perfectly in a Daimler-Benz Panther without adjustment. This meant logistics complexity, increased spare parts inventory requirements, and field maintenance challenges that American forces simply didn't face. The diesel-powered M4A to particularly impress German engineers. Soviet forces received 4,102 of these tanks through Lend-Lease, and significant numbers fell into German hands during fighting on the Eastern Front. The twin GM 6046 diesel engine provided performance matching any Sherman variant while consuming substantially less fuel than gasoline engines. A critical advantage as German fuel supplies dwindled. German designers had experimented with diesel tank engines but abandoned the effort due to manufacturing difficulties and the complexity of reliable fuel injection systems at the compression ratios required for good diesel performance. American industry produced diesel Shermans alongside gasoline variants without disrupting production schedules, demonstrating manufacturing flexibility and technological sophistication that German industry never achieved during wartime conditions. The British Firefly variant, which mounted the 17-pounder anti-tank gun in a modified Sherman turret, demonstrated another American advantage that German engineers hadn't considered when specifying their vehicles: growth potential. The Sherman's large turret ring accommodated the significantly larger British gun with minimal modification. The basic chassis handled the increased weight without powertrain modifications. The Panther, rushed into production to counter Soviet T-3 for tanks, had no capacity for significant armament upgrades without complete turret and vehicle redesign. The vehicle had been designed to precise specifications with minimal margins. There was no extra capacity to accommodate heavier weapons or increased armor without degrading the already marginal powertrain reliability. The Sherman, with its generous design margins and robust construction, could accept modifications and improvements that the original designers never envisioned. This flexibility, which seemed like wasteful overbuilding to German engineers calculating material efficiency, proved invaluable when battlefield conditions demanded changes. March 1944 brought reports from General Heinz Guderian, Inspector General of Panzer Troops, noting in official communications that improvements to Panther reliability had achieved what he termed acceptable standards by early 1944. Engine life had reached 700 to 1,000 kilometers. Final drive problems had been largely resolved through design modifications and improved manufacturing processes. This improvement presented a significant success in German military communications, merely brought Panther reliability to a level Sherman had exceeded from initial production in 1942. The German army celebrated reaching standards that American tanks had met 2 years earlier. This gap, more than any battlefield defeat, revealed how far behind German armored vehicle development had fallen. The comparison grew more painful as German tank production struggled with increasing resource shortages and Allied strategic bombing. The bombing campaigns targeted key bottlenecks in the Panther and Tiger production chain with increasing effectiveness. The night of April 27th to 28th, 1944 brought devastation that German tank production never fully recovered from. Royal Air Force Bomber Command launched a raid on Friedrichshafen, involving 322 aircraft. The target was the Maybach engine plant. The raid succeeded beyond the planner's expectations. The Maybach engine plant suffered severe damage that halted production completely. The ZF gearbox factory, located adjacent to the engine plant, was also destroyed. Production of tank engines and transmissions stopped for 6 months. When manufacturing finally resumed in November 1944, quality control had degraded significantly. Slave labor, increasingly employed in German factories as German workers were conscripted for military service, introduced deliberate sabotage, cigarette filters jammed into oil passages, gaskets installed incorrectly, components assembled without proper clearances, bolts deliberately cross-threaded. These sabotage efforts, impossible to detect without complete disassembly, turned even newly built German tanks into ticking time bombs. None of these problems affected Sherman production. American factories operated safely across the Atlantic, far from any combat zone. They were staffed by motivated workers earning good wages under decent conditions. Quality control remained consistent. Material supplies never failed. The industrial advantages that testing at Kummersdorf had revealed in German tanks' mechanical systems were mirrored in the broader industrial context. The fundamental difference between American and German tank production lay not in engineering knowledge, but in industrial capability and underlying design philosophy. German engineers understood automotive principles as well as their American counterparts. They possessed extensive theoretical knowledge and scientific expertise. They simply never applied those principles consistently to tank design, instead prioritizing other factors. German tanks emphasized performance, characteristics that made for impressive specifications but poor reliability in field conditions. The Panther's powerful 75mm KWK-42 gun and thick frontal armor came at the cost of an overtaxed powertrain that couldn't reliably support the vehicle's 45-ton weight. The Tiger's formidable capabilities demanded complex maintenance procedures and frequent repairs by highly trained specialists, who were becoming increasingly scarce as the war continued. These trade-offs might have been acceptable if German industry could produce enough vehicles and enough spare parts to maintain them. It could not, and as Allied bombing intensified and raw material shortages worsened, the gap between German capability and German ambition widened into an unbridgeable chasm. American engineers, trained in automotive mass production through decades of civilian industry experience, designed tanks that could be manufactured by the tens of thousands and maintained by mechanics with basic training using skills learned in civilian life. The Sherman powertrain used components proven in commercial service. Design principles were borrowed directly from automobile and truck manufacturing. The electrical system included backup systems that seemed like unnecessary luxury to German designers but proved invaluable in combat. German designers never considered these features high priorities. Compared to armor thickness and gun power, they designed for specifications that would impress senior officers in briefings. Americans designed for specifications that would keep vehicles operating in the field. Which approach better served the actual requirements of mechanized warfare became obvious to anyone willing to examine the evidence. Objectively, by spring 1944, Wehrmacht units on all fronts reported increasing mechanical problems as manufacturing quality degraded and spare parts became increasingly scarce. The situation had progressed beyond concerning into catastrophic. Panthers required transport by rail for movements exceeding 100 kilometers because their final drives couldn't survive sustained road marches. Field commands issued explicit orders restricting Panther movement to preserve the vehicles for actual combat rather than losing them to mechanical failure during approach marches. Tank commanders had to balance the tactical need for armor against the near certainty that moving Panthers any significant distance would result in breakdowns. The Berg Panther recovery vehicle, built on a Panther chassis specifically to recover disabled Panthers, shared the same reliability problems as the tank it was supposed to recover. German commanders faced the grim absurdity of recovery vehicles that needed recovering, creating logistics nightmares that paralyzed entire formations. Some units reported that 70% of tank losses were due to breakdowns rather than combat damage. 70%. More than two-thirds of German tanks were being eliminated by their own mechanical failures, not by enemy action. Crews would abandon perfectly good armor and guns, because the powertrains had failed and no recovery was possible. Meanwhile, Sherman production continued at unprecedented rates that German industry could never match. American factories produced 49,324 Sherman tanks during the war. That number exceeds all German tank production of all types combined. British Commonwealth forces,